f of t comma y be 2y plus e to the ty. Okay. Period. So the partial. Now wait a minute. Taking the part at f, we're taking the partial with respect to t this time. Respect to t. All right. So let's see that. So there's a partial with respect to t of f of t comma y. Oh, that's nice. The derivative of 2y with respect to t, that's just a constant, so that's a 0. Oh, and now here's t, there's a function that also has a t, so we have a product. So the derivative of t is 1 times the second, which is e to the ty, plus the second, which is a t, times the derivative of the second, that's going to be e to the ty, and now it's t is the variable, so what's the derivative of ty? Y. Is that exact? Wait a minute. That is that, isn't it? Yeah, it sure is. So in other words, all that is the same as partial with respect to minus, I've got the minus sign, is equal to minus the partial with respect to y of g y. So the equation is exact. I hope that this all fits in the last bit of space. I always hate erasing all this good work that we do. So I think the process, when you see this, you're like, that's pretty slick. It takes some pretty concentrated thought to get through it, but once you see it, you're like, oh, that was really neat. That's always been my reaction to it. Hopefully yours is even better than that. I don't know. Let's see. So notice this. At this point, point 2 is we can solve it. So 2 is solve. And we'll say solve since it is exact. Here's what it was. F, you can start with G, or you can start with F. It works either way. I'm going to start with G, or with F, just because it's the positive one, and then we'll use the G, because we have to include that negative sign for the second part of it. Remember we talked, there was an original function, some capital T of t and y, and F was the derivative with respect to what? Y. So in other words, if we take, if we take the antiderivative with respect to y, that should get us pretty close to the original equation, t plus some constant. Now I know in 4a you guys did a very similar problem, so this may seem familiar, and you'll see where this happens. So let me write that down. Is what we're going to do is recall. Yeah, this is going to take more than this. But recall f of t and y came from the partial of t with respect to y. So integrate that. Integrate integrate f of t comma y dy. Let's see what we get. That's where we're going to start. So I'm going to write the integral, and you're going to love this. I don't know what you will like. Just leave that off. We'll just show you. So we want to take the integral of f. F we said was 2y plus t e t y dy. Okay, we're taking the integral of that with respect to y. I think we're going to get a y squared plus, oh, t is a constant, isn't it? T is a constant. So the only y, this is, just think of this as e to the ay, if you will. So I would need to divide by my t, my coefficient, my singular here. And I think I would have that. So I'd have t over, divide by a t, e t y plus. Now, here's the tricky part. Okay, I'm going to write this. C of. C, this stands for a constant. I'm going to put a special constant. Okay, remember, these are indefinite integrals. So if you're going to integrate this way, you have to add a constant. But now think about this. When you first learned to integrate, how did you check your answer? You take its derivative. If I take the derivative of this with respect to y, I would get 2y. If I take the derivative of this with respect to y, I would get this. But what about that? If I take the derivative of this with respect to y, I've already accounted for that term. I've accounted for that term. What should this be? The derivative of this should be z, or 0, right, z for sure. Should be 0. So this has to be, if this was a function of y, the derivative wouldn't be 0. But if it was the function of t, what would it be? 0. It would be 0. So we can write this as some constant that's a function of t. Isn't that clever? What? You did. I don't remember. It was like I was eating it down. That's how we got there. Yeah, this is the same. Okay. So here we go. Now, this, what is this? This is almost that original problem, capital T of Ty. Wait a minute. So if this is really T of t comma y, the partial of this with respect to y gave me f. The partial of this with respect to t should give me g. It should give me g. So here's what we do. We take the derivative, or the partial derivative with respect to t. With respect to t of all this, so y squared plus, what is t over t? 1. Okay. You guys are holding out on me. You're not even sure anymore. You're so confused. Like, I thought that was 1, but today it might not. And now in this case, this is why we had to do this. It's not going to be g. It's going to be, look over there. It has to be minus g. So we're going to put minus g of ty, which is going to, remember we put the, here's our minus. So if I minus g of ty, I'll write it all out. Minus 1 minus t e. Oh, it is. You're right. Y. That's right. You had a feeling something. And so let's just clean this up. So if I take the partial of the left-hand side with respect to t, the partial with respect to t of y squared is 0. The partial of e to the ty becomes yeah, y e to the ty plus the derivative with respect to t of c. And you might be like, how come you're not using the partial notation? You don't have to, you can. If you're not using it though, is this is only a function of t, so writing the partial derivative or writing the derivative in this form is the same thing. This has to somehow equal 1 plus y e ty. I know many of you have been trained not to do this. I don't care. I'm going to do it now. Just cross the yes. Oh, because this, we are so close. The derivative, how would we solve this? We just integrate that last step. And so we take the integral of the derivative with respect to t of our special constant dt is equal to the integral of 1 dt. And so we can say that c of t is equal to t. Okay, c of t is equal to t. And here's what we write. Our final function is some function t of t comma y equals y squared plus e to the ty plus t. And here's what we would normally write. We write equals some constant c, actually put plus c. So when you put this over here, it's minus c, but this could just be another c. You do the c1 through 11 again if you want. You get that here. What was the c going to represent? It would represent your initial conditions. So if I started, if I find t of 0, y of 0, I would have y of 0 squared plus e to the 0, that would be 1. That would be a 0 equals c. So you can say that your function t comma y is y squared plus e to the ty plus t is equal to y of 0 squared plus 1. Isn't that the slickest thing? I think so. Yes, all right.
So, right there at the beginning where we said recall that f of t comma y equals the partial of capital T.
Oh, this part, yeah. Okay.
Like, would we have gotten to the same place if we used the other side?
Yeah, you would. But remember that minus sign on the you're going to need to include that, so you want to use it as minus, and then take the derivative, the integral of g with respect to t. Yep, and then there's, or I guess you put the minus on the other side and deal with that later. But yeah, and I would encourage you to try it too. It should work either way. And so then, if you did that, so if you took the integral of g with respect to t, and you went through this, your function now becomes, your special constant becomes a function of y here, and then you would follow this step. Okay.
Did you ever explain why that was needed?
It's right here. It's because our problems are going to be set up in this form, and so if you just rearrange them, you pick up the minus. Yeah, they have to match, to be exact. Yes, it would. But we're splitting the differentials to remember what parts they came from. So, in other words, the differential in this piece here has to match, has to be, this whole piece here has to match the whole partials of that. That takes a little bit of, think about it for a minute, try this. I have. So that's the end of chapter 1. That's the end of the material for our test. So our test will be not this Wednesday, but 1 week from Wednesday. I'll be honest, the test will focus more on the later chapters than or the later sections than it will on the earlier sections. I know I spent a lot of time about what is so significant about E. Maybe I didn't need to, but the test will be more about starting on section 1.4. How do you solve these things? How do you find a steady solution? Things like that. And then let me give you some practice. 1.8. All right. I don't think I have this posted yet. I'll have it shortly. 1.8. 1, 2, 4. Eight, 10, 11, 12, 13, 14, and that's 20. All right. So, for those of you who like, we're going to head over to the math lab for office hours. Otherwise,